Hi, thanks for tuning in. My name is Amelia Averett, and today I will be discussing adversarially learned balancing weights for causal inference. In this talk, I will present my new deep learning model, the Counterfactual ChiGAN, which supports causal inference from 2 or more cohorts. I will present the model, give some intuition about how it works, and present my experimental evaluation. Currently, I work on the clinical informatics team at the Regeneron Genetics Center, but this research was completed during my doctoral candidacy at Columbia University's Department of Biomedical Informatics. There are many definitions of causal inference, but my favorite is by Voigt, and he very simply describes it as the process of drawing a conclusion about cause and effect relationships. In biomedicine, the preferred framework of causal inference is the counterfactual. Counterfactual reasoning leverages if clauses that are contrary to the truth to investigate what would have happened had the world been different. In this framework, we have a group treated with the exposure of interest and a comparator group that's the same in every way to the treated group except in the treatment itself. We then compare these two groups and gain insights about the relationship between the exposure and the outcome. Perhaps the most common counterfactual model is the Rubin causal model. And under this framework, causal estimates are unbiased when two assumptions are met. The first is the stable unit treatment value assumption, or SUTVA, which is essentially non-interference and is assumed to be true. And the second is strong ignorability. This assumption states that a treatment's assignment is unconfounded and therefore ignorable. This has the important consequence of making features in both the treatment and comparator arms equal in their distribution. But because SUTVA is assumed, we really just look to enforce strong ignorability in our data to produce good causal estimates. So how do we uphold strong ignorability to produce valid causal estimates? We ensure feature balance. Balance here refers to the similarity of the full feature distribution between two arms. In this circumstance, all important factors of variation should be equal in the treatment and comparator cohorts, and the only thing that remains different is the presence or absence of the treatment. In health, we often achieve this by approximating with a randomized controlled trial, or RCT, in which randomization ensures strong ignorability. But in the absence of randomization, such as in observational data, manipulation is required to enforce this assumption. There are a lot of ways to do this. The most popular methods are matching, adjustment or stratification, and weighting. I am interested in discussing weighting today. But what is weighting? If we have a sample and a population, or in our case, two arms of a trial, that don't look like each other, we can disproportionately consider units in one arm to look more like units in another arm and vice versa. And this means applying larger weight to individuals who are underrepresented and lower weight to individuals who are overrepresented. We can then utilize these weights when considering each unit's contribution to expectations, such as the average treatment effect. This is called a natural experiment, in that we've created a population in which units could theoretically be assigned to either treatment arm based on their features, and thus strong ignorability is upheld. The idea of weighting is actually very related to importance sampling. And importance sampling is a process that draws samples from a proposal distribution, Q, and reweights that distribution using important weights so that the weighted distribution represents your target distribution. Inverse probability of treatment weighting, or IPW, is the most widely used weighting method in biomedicine. In this method, units are weighted according to the inverse of their probability of being assigned to the treatment conditional on their measured baseline features. This is often called the propensity score. However, these weight estimates are very dependent on the model used to estimate them, and weights can be very unstable and actually cause feature imbalance or bias if the propensity score is very close to 0 or 1. A method that learns stable feature balancing weights in a more model agnostic way is preferred. So, how can we learn balancing weights for causal inference such that the weights are more stable and model agnostic? I think we could use a generative adversarial network, or GAN for short. GANs are well suited for modeling weights because they are implicit generative models, and these models only specify a stochastic procedure with which to generate data. This is opposed to prescribed models, which provide explicit parametric specification for the distribution that you're modeling. Implicit generative models, like GANs, are particularly attractive for modeling weights because we can do so without making any assumptions about the underlying probability distribution. This could make weights estimated from this procedure less prone to instability originating from model specification. The most simple GAN is called the vanilla GAN, and it simplifies this often troublesome task of modeling a generative distribution by pitting two neural networks against each other in a zero-sum game. The vanilla GAN is comprised of a generative neural network, G, which makes samples from a target distribution, and a discriminative model, D, which estimates the probability that a sample is real rather than generated from G. The goal of G is to produce increasingly convincing forgeries, and the goal of D is to become increasingly good at detecting forgeries. Ideally, at the end of training, G wins and forged samples are indistinguishable from real data. This minimax game is summarized by the formula at the bottom of the screen, and note that this solution minimizes the Jensen-Shannon divergence. But the vanilla GAN architecture won't suffice for learning feature balancing weights, so we need something new. Recall that in a weighting method with a treatment and comparator, our goal is to downweight individuals who appear too frequently in a single arm, and we want to upweight people who do appear in both arms but their prevalence is not equal. In our case, with a treatment and comparator, after weighting, this upweighted population could have potentially gone to either arm, just like a natural experiment. I imbued this logic into my model, the Counterfactual ChiGAN, or CGAN for short. It differs from the vanilla GAN in two important ways. First, and most obviously, it is a single generator which feeds two discriminators rather than one, as we saw earlier. These discriminators are fed by the two populations that we would like to contrast. The second difference is that this model minimizes the chi divergence instead of the Jensen-Shannon divergence. I use the chi divergence because minimization of this results in minimal variance in important sampling estimates in downstream expectations. But using this divergence in our model requires a modification to the discriminator. I use previous work by Noetsen et al., which specifies variational functions that can be easily incorporated into the GAN objective function by replacing the discriminators. These variational functions can then be evaluated directly to calculate important sampling weights for each population. But for ease, I will continue to refer to these networks as discriminators and denote them by D. During the training procedure, units are sampled from the treatment and comparator groups, population 1 and population 2. The complete set of features for each sampled unit flows downstream into their respective GAN. At the same time, the generator produces a single set of simulated features, which each discriminator then compares to the sampled unit's features. Over many iterations, the discriminators and generator will be trained such that the features from the treatment and comparator cohorts will become increasingly difficult to distinguish, or in other words, the features will be balanced. I can then directly evaluate the important sampling weights from each discriminator as a byproduct of the variational functions, and these may be applied directly to features as a multiplicative to ensure feature balance. To evaluate the counterfactual ChiGAN, I applied the model to simulated data in which the ground truth is known, and an application to real-world clinical data from the Columbia University Electronic Health Record. I'll begin by discussing the simulation. In practice, development of a model and assessing whether or not the CGAN can actually learn feature balancing weights is carried out through a simulation in which the ground truth is known. This involves constructing two cohorts in which the overlapping populations are known and pre-specified, applying the CGAN and then interrogating the weights of overlapping population and the non-overlapping population. Here is a schematic of the simulation that I implemented. I used two arms of the simulation, POP1 and POP2, but it is worth noting that the model can actually be implemented to inquiries between more than two groups. I began with three subpopulations, A, B, and C, which were drawn from randomly generated multivariate normal distributions, each comprised of 5 discrete and 5 continuous features. I constructed POP1 and POP2 such that part of both arms was born from the same subpopulation. POP1 was a mixture of data from subpopulation A and subpopulation B, and population 2 was a mixture of data from subpopulation A and subpopulation C. 2,000 features were drawn from each subpopulation for each arm, so there were 4,000 units per arm. So I also simulated a binary outcome which was conditional upon the subpopulation of origin. And I just want you to make a mental note that the naive ATE, or average treatment effect, from the mixture population, so POP1 versus POP2, is 50, and the ATE from overlapping populations over which the counterfactual inquiry is appropriate over just subpopulation A is 70. To make sure that this model is super robust and performance is consistent over all of the parameters that I've outlined, I additionally conducted a sensitivity analysis in which I varied the per-arm sample size, the unbiased average treatment effect that exists between subpopulation A in both arms, and the proportion of overlap. To evaluate the simulation, I will be presenting a visual inspection of our data, an assessment of the bias in the average treatment effect estimates, and an inspection of the effective sample size, or ESS, to ensure that there is no mode collapse. To contextualize this evaluation, I additionally implemented these weighting methods and will contrast their performance with the ChiGANs. So, these are a few results from the simulation. These are 2D projections of a few select feature combinations. I'm going to walk through these together with you, so don't panic. But I just want you to know that these images demonstrate the relationship between the setup of the simulation, the generator, and the weights. The first plot shows the data for population 1, orange dots, and population 2, the green pluses. In the second plot, I've highlighted the data generated from subpopulation A in purple. These purple areas denote the data that has feature balance between population 1 and population 2. In the third plot, I've taken a few samples from my fully trained generator and plotted it over the data from plot 1. This is in blue. Finally, in the last plot, I have the data from population 1 and population 2, just as it was in the first plot, but I've adjusted the transparency by the normalized weights from the counterfactual ChiGAN. So the darker or brighter the point, the higher the weight, and the lighter the point, the smaller the weight. And what I hope you can see here is that the region with the high weights is the same as the region as the generator and is the same as the region in subpopulation A. This is compelling evidence that the structure of the model encourages the generator to identify the distribution that overlaps the populations, and the model learns weights such that units from this overlapping population have high weights and units outside of the overlapping population have low weights. When evaluating the ATE, recall that by the simulation, the naive estimate over just the mixture population is 50, but the ATE in the overlapping population in which counterfactual analysis is appropriate is 70. So, to determine if the ChiGAN is better at estimating an unbiased ATEs, I implemented the comparator weighting methods that are listed here and applied those weights to the outcome data to learn each model's ATE. The results are shown here, and you can see that the ChiGAN is nearest to the true treatment effect with an ATE of 70.01, which indicates that the ChiGAN may yield less biased effect estimates than comparators. And if we take a look at the effective sample size, we see similarly good performance. The ChiGAN has an effective sample size, or ESS, of 3,870. Given that there were 4,000 units that are comparable across the two arms, each subpopulation contains 2,000 units, this is an appropriate estimate. In the sensitivity analysis, in which I have varied these parameters of the simulation, we saw similarly good performance of the ChiGAN in both of these domains. Next, I'll very briefly describe the application of the counterfactual ChiGAN to real-world clinical data. To address this research question, I created observational cohorts according to the indication, intervention, and comparator of a published randomized clinical trial. I've chosen the sitagliptin and glimepiride trial by Harvey et al. For this experiment, as my features, I opted to use laboratory measurement with the least amount of missingness. There was a natural hinge in the frequency of labs, so I took the top 37, which occurred most frequently. If there were repeated measurements, I took the most recent, and if there was missing data, I made a single mean imputation. I then applied the ChiGAN and all of the comparator methods from the previous aim to this data. To evaluate, I compared the feature balance in the unweighted counterfactual ChiGAN and comparator-weighted cohorts. I quantified feature balance using the absolute standardized differences in the mean, or the ASDM. Its name is exactly what it is, but I've included the formula here for your reference. A lower ASDM means the treatment and control are closer to each other, and this is indicative of good feature balance between arms. Here are the results of that experiment. On this plot, the 37 features are on the left-hand side, and the ASDM is on the x-axis. Recall that closer to 0 is better. The per-feature ASDM from the data weighted according to the ChiGAN is in orange, and the unweighted ASDM is in gray. All other comparator methods are in shades of blue. I recognize that this might be a little difficult to read, so I've summarized the mean ASDM across all features for all comparators. The unweighted ASDM was 0.1103. The ChiGAN produced the lowest ASDM of 0.0364, which indicates that our method was the best at achieving feature balance. To conclude, the experiments that I've shared with you today suggest that the counterfactual ChiGAN is an effective method of learning feature balancing weights. Recall this image that I referred to earlier. The experiments I've shown to you today demonstrate that individuals who are not directly comparable will be assigned a negligible weight by the ChiGAN, and individuals for whom the treatment assignment is effectively random will have high weights. The results of this simulation and application to clinical data demonstrate that this counterfactual-like population is appropriately identified, upweighted, and that weights on these individuals can be used to encourage feature balance. In total, these results imply that the ChiGAN could provide an alternative means to causal inference from observational data. And if all confounding variables are observed and included as features, the average treatment effect estimates from ChiGAN-weighted cohorts may be less biased than estimates from current weighting methods. The ChiGAN and its related aims do have some limitations. Notably, ChiGAN training is known for being unstable, and assessing convergence is not a standardized procedure. In the best-case scenario, we would want to compare ChiGAN-weighted ATEs with the gold standard, which is the randomized controlled trial effect estimates. However, we found that the experimental setting from the RCT was so markedly different from our observational data that effect estimates between these two data sources would never be comparable. This research is published and available through JBI. You can access it with this QR code. Here, you will also find references for this work. And to close, this research was funded by grants from the National Libraries of Medicine. Thanks for your time, and if you have any questions, please feel free to reach out to me via any of these methods on the screen.